The common ion effect, limiting of ionization by simultaneous ionization. In a strong electrolyte, I will have approximately 100% ionization of any of my substances. Weak electrolytes will come to an equilibrium process. So for example, if we have acetic acid forms an equilibrium when dissolved in water such that some of the acetic acid will ionize and form hydronium and acetate. The rest will remain as acetic acid. And the reaction comes back and forth to the point where I get a mixture of all four of these in solution. If I add an ion to the equilibrium from some other source than the initial ionization, it will change the concentration. For example, if I add sodium acetate, that produces acetate in my solution. According to Le Chatelier's principle, if I add product, it will shift equilibrium toward the reactant. So looking at the above equilibrium process, if I'm adding in acetate from something like sodium acetate, I'm adding to the product on the right-hand side. This is going to force the reaction to move towards the left. As it moves towards the left, that means I'm limiting the ionization of my acetic acid. The more acetate I add from another source, the less acetic acid gets ionized, and in the end I wind up with a lot of acetic acid and a lot of acetate in solution at the same time. The two reactions which occur overall are the dissolution of sodium acetate to form sodium ion and acetate ion, and the equilibrium ionization of acetic acid to form hydronium and acetate. Seeing here, we have acetate in two different places. We add this together to get the total amount of acetate that's formed. So it's coming from both. The acetate comes from both sources, and it shifts the equilibrium of the reaction to the left. Now, buffer solution is a particular application of the common ion effect. It's one of the most common applications. A system can maintain a relatively stable pH using what's called a buffer. And a buffer generally consists of either a weak acid and the soluble salt of its conjugate base, or a weak base and the soluble salt of its conjugate acid. An example of a buffer solution would be acetic acid and sodium acetate being added together. The effect of the common ion effect minimizes the acid ionization, because the ionic solution will be 100% ionized and the acid will be minimally ionized, we wind up with the ionization suppressed according to Le Chatelier's principle. This creates a large amount of both the acid and its conjugate base in solution at the same time. So we have our equilibrium process here. We have high amounts of acetic acid on the left and high amounts of acetate on the right. We're kind of limited oftentimes in the amount of hydronium that's formed, but we'll generally get, the amount of hydronium will depend upon the relative ratios of the two species. So as an example, if I have a 0.1 molar acetic acid solution, that would be generally 1.29% ionized with a pH of 2.89. I can calculate the percent ionization and pH of a buffer solution of 0.1 molar acetic acid and 0.2 molar sodium acetate. The Ka of acetic acid is 1.8 times 10 to the negative 5. Now the first process is the dissociation of sodium acetate to form sodium and acetate. Because this is about a 100% process, our 0.2 molar sodium acetate will produce 0.2 molar acetate ion. Our other process is the equilibrium of the acetic acid and the acetate. The initial concentrations will be 0.1 for acetic acid and 0.2 for acetate, because that 0.2 comes from the dissociation of the sodium acetate. Our change will be minus x, and plus x. So we get an equilibrium of 0.1 minus x, and 0.2 plus x. Our Ka value is the acetate times hydronium divided by acetic acid, with a value of 1.8 times 10 to the negative 5. If we plug in our equilibrium values, we get 0.2 plus x times x divided by 0.1 minus x. Now, assuming x is negligible, we wind up with 1.8 times 10 to the negative 5 being equal to 0.2 times x divided by 0.1. Multiplying both sides of the equation by the reciprocal of 0.2 over 0.1, we get 0.1 times 1.8 times 10 to the negative 5 divided by 0.2 as our x value. This gives us 9.0 times 10 to the negative 6. That becomes our hydronium concentration. As an ionization, 9.0 times 10 to the negative 6 divided by 0.1 as a percentage is only 9.0 times 10 to the negative 3% ionized, or 0.009%. That's not much at all versus our 1.29. If we compare it to the 1.29, it's only 0.698% of the original ionization from acetic acid by itself. The pH will be the negative log of the hydronium concentration, at 5.05. Compare that to the original pH of acetic acid at 2.89. So the minimal ionization means that the acid and its conjugate molarities are approximately the same as their starting molarities. So since the acetic acid started at 0.1 molar, it pretty much ends at 0.1 molar. The sodium acetate, the same, started at 0.2, ends at 0.2. Henderson-Hasselbalch equation. The assumption that we just made holds true for any dilute weak acid or base in its conjugate system. Generically speaking then, an acid plus water will ionize to form its conjugate base and hydronium with a Ka value equal to the conjugate base times hydronium divided by the acid. I can rearrange this to solve for the hydronium concentration such that hydronium will be equal to the acid divided by its conjugate base times Ka. If I take the negative log of the entire equilibrium expression, we'll get the negative log of hydronium equals the negative log of the HA times Ka over A minus. Now we know that negative log of hydronium is pH, so we can substitute that back in so that pH equals negative log of HA over A minus. Any sort of multiplication process in a log can be separated out as an addition. So I can take the negative log of HA over A minus and add that to the negative log of Ka. Because I'm adding a negative, it just becomes a minus, so we get negative log of HA over A minus minus the log of Ka. Now we know that minus log of Ka is pKa. I can substitute that in, so now I have pH equals negative log of acid over conjugate base plus pKa. If I swap the sign of the log to make it a positive, I simply will invert what is inside of the log. So I wind up with pH equals the log of the base over the acid plus its pKa. I can rearrange this such that pH equals pKa plus log of conjugate base over acid. This is called the Henderson-Hasselbalch equation. It can be used to calculate buffer pH. Our previous solution of 0.1 molar acetic acid and 0.2 molar sodium acetate, if we have the negative log of our Ka, that's 4.74. So our pH would be 4.74 plus the log of the conjugate base, 0.2, over the conjugate acid, over the acid, 0.1. So 4.74 plus the log of 0.2 over 0.1 gives us 5.04. Which is about the same pH as what we calculated by the ICE formula at 5.05. There's an analogous equation for bases, which involves the base equilibrium and the pKb, where base produces the protonated base plus hydroxide. The Kb value would be the protonated base times hydroxide over the base, and in this case we use a POH instead of a pH because we're given OH minus as our species here. So it looks just like the Henderson-Hasselbalch equation for acids, except it's the POH, the pKb, and the conjugate acid over the base. So if I have a 0.2 molar ammonia solution and a 0.1 molar ammonium chloride solution combined, our equilibrium is like this. If we're looking for the POH would be the pKb. If the Kb is the same as acetic acid, its pKb is 4.74. Plus the log of the ionized species, 0.1, over the base, 0.2. Adding that together would give us 4.44 as our POH. The pH then would be 14 minus the POH, or 9.56. So we can confirm what we just demonstrated looking at ammonia. A 0.1 molar solution of ammonia by itself would be just like acetic acid, 1.29% ionized, and its pH will be 11.11. We can calculate the percent ionization and the pH of a buffer solution of the 0.1 molar ammonium chloride and the 0.2 molar ammonia. In the initial process, the first one will be the dissociation of the ammonium chloride. 0.1 molar ammonium chloride will produce 0.1 molar ammonium. We can then look at the equilibrium of ammonia and ammonium, where the initial concentration of ammonia will be 0.2. Ammonium will be 0.1 from the ionization or the dissociation of the ammonium chloride. Our change will be minus x plus x and plus x, which gives us 0.2 minus x, and 0.1 plus x. We have the same general Ka expression, except it's a Kb now. So ammonium times hydroxide over ammonia, that equals 1.8 times 10 to the minus 5, which equals, plugging in our equilibrium values, 0.1 plus x times x divided by 0.2 minus x. Now assuming x is negligible, we get 1.8 times 10 to the minus 5 equals 0.1 over 0.2 times x. Multiplying by the reciprocal on both sides, will give us an x value equal to 3.6 times 10 to the minus 5. As a percent ionization, divide that by 0.2. As a percentage is 1.8 times 10 to the negative 2% ionized. Comparing that to the initial ionization, it is only 1.4% of the initial ionization of the ammonia by itself. The pOH of the solution will be the negative log of 3.6 times 10 to the minus 5 at 4.44. Subtract that from 14, we get a pH of 9.56, just like we said when we did the Henderson-Hasselbalch equation on this. Now compare 9.56 pH to 11.11. It's much reduced from the standard base. Minimal ionization means that the base and its conjugate molarity, again, are roughly what they start at, 0.1 for the ammonium and 0.2 for the ammonia. Now buffering action allows a solution to resist pH change. Any sort of buffer situation like this, the addition of a strong acid will produce hydronium. The equilibrium will shift away from the hydronium towards the left. Adding a strong base will remove hydronium. Equilibrium will shift to replace that hydronium, shifting to the right. A buffer contains a high amount of an acid and its conjugate base in concentration. So for example, if I take hydrochloric acid, the acetate ion is much stronger as a base than chloride. This will cause the neutralization of the H3O plus that's added by the reaction of the acetate with the hydronium, whereas the chloride would not be able to do that. Overall, this causes the concentration of hydronium to change very little because most of what gets added gets neutralized. This will continue so long as both species are in solution. As soon as I run out of whichever one is having to react at the moment, my buffer will break down. If I'm adding a base, the acetic acid will deprotonate to replenish the hydronium that is reacted away. If I'm adding an acid, the acetate will react with the hydronium to produce acetic acid. So as an example, what is the change in H3O plus and the pH from adding 0.01 mole of sodium hydroxide to a 1 liter buffer solution that is 0.1 molar in both acetic acid and sodium acetate? Our starting pH is 4.74 plus the log of 0.1 over 0.1. Now, 0.1 over 0.1 gives us a log of 1. Log of 1 is 0, so anytime I have an equal amount of my acid and its conjugate base, my pH will equal the pKa. We have the initial dissociation to produce hydroxide. We get 0.01 moles of hydroxide. My species that I'm concerned with for the Henderson-Hasselbalch equation are the OH minus, the acetic acid, and the acetate, because OH minus determines how much acetate gets produced. Our starting concentrations are 0.1 for acetic acid and 0.1 for acetate and 0.01 for hydroxide. We lose 0.1 hydroxide. That takes away we lose 0.01 hydroxide. We take away 0.01 from the acetic acid, and we gain 0.01 in the acetate. So we wind up with final concentrations at equilibrium of 0.09 for the acetic acid and 0.11 for the acetate. Our new pH, according to the Henderson-Hasselbalch equation, is 4.74 plus the log of 0.11 over 0.09, which is a pH of 4.83. So we get to jump up from 4.74 to 4.83, which is not a huge jump. Compare this to adding that directly to a 0.1 molar solution of acetic acid. If I added that same sodium hydroxide to just acetic acid, I would have still 0.09 molar acetic acid. I would get 0.01 molar acetate. The pH would be 4.74 plus the log of 0.01 divided by 0.09, which is 3.79. The standard pH of acetic acid is 2.89. That's a big jump, almost 1. Adding it to water is even worse. The negative log of 0.01 is 2, so the pH from the pOH of 2 is 12. We get a jump from the pH of 7 to pH of 12. Minimal change in pH, then, we can see occurs with a buffer, but it's much larger with the other two. And keep in mind that every jump in a pH unit is a 10-fold jump in concentration.